Okay, this is sample problem 19.4. Calculate the standard free energy change for the following reactions, or reaction, I'm sorry, at 25 degrees C, right, 298 Kelvin. So they give us the equation. It's 2 moles of gold, solid form, plus 3 moles of calcium 2 with a concentration of 1 molar, in equilibrium with 2 moles of gold 3 at a concentration of 1 molar plus 3 moles of calcium. And they want us to find delta G for this reaction, okay? So in this section, what we do, or one of the things we did, was we connected the cell potential to the standard free energy change. So what we said was, of course it says standard, so that means you put the degree sign, is equal to minus n, where n is the number of moles of electrons transferred, times F, which is Faraday's constant, times the standard cell potential. So we need 3 numbers to calculate the standard free energy change. Okay? Notice the concentrations are 1 molar and the temperature is 25 degrees C. The reason for that is because we're under standard conditions. If we're going to calculate delta G standard, delta G naught, then we have to use the standard cell potentials, and the standard cell potential is based on the standard reduction potentials, which are given under standard conditions and at 25 degrees C. So let's put in what we know already. We know this is a negative. We don't know the number of moles of electrons transferred in the equation yet. We'll figure that out. But we do know this value of F is 96,000, so either 500 or 485, whichever, how many sig figs you want. And the units for that is coulombs per mole. And then we need to find the cell potential. The cell potential is in volts, right? E is in volts. But remember from the discussion of the lecture here, a volt is a joule per coulomb. So it's going to be whatever the volts are, but joules per coulomb would be the units. Okay? So what will happen is the coulombs will cancel, and then that's going to give us some number that's in joules per mole. Not kilojoules per mole, but joules per mole. The next step then is to figure out what the cell potential is. And this goes back to the earlier sections. The cell potential is equal, we're going to do standard conditions, to the standard cathode potential, reduction potential, minus the standard reduction potential of the anode. Okay, we learned how to do that in section 19.3. So the problem, not the problem, but one of the issues that we're dealing with here is we have to figure out which one's the cathode and which one's the anode. So here's how we're going to do it. We're going to take the overall equation and we're going to split it into 2 half reactions. So 2Au solid goes to 2Au plus 3, right? It says plus 3 there. Now we balance the equation. Gold is going from 0 to plus 3. We add the electrons to the more positive side, but there's 2 of them, right? So it's 3 electrons for each gold, but there's 2 golds, so that's 6 electrons. Okay? So that's what's happening there. Now you ask yourself, is that reduction or is that oxidation? That's oxidation, right? And oxidation, there's a lot of information in the previous 2 sections. Oxidation means that it's the anode. So what we do is we look up that potential for gold, and I'm not going to show it to you here, but I'm going to give you the voltage looking it up. It is 1.50. Okay, so we're going to use that potential 1.50. Now, let's do the cathode. If this is the anode, the other one's got to be the cathode, right? But let's prove to ourselves that's true. 3 calcium 2s is going to 3 calciums, solid, right? I'm just taking that from the equation up in the question. So now, if you have 3 calcium 2s and it turns into 3 calciums, how many electrons? had to get added. 3 times 2 is 6. So there's more positive charge on the reactant side by 6. So we have to add 6 electrons. So the fact that the equation up at the top is balanced helps us because it gives us the same number just as a matter of fact. Okay? So now we look up the calcium, and it turns out the calcium is way down at negative 2.89 volts. Again, that's from, these values I'm getting here are from table 19.1. Okay? The standard reduction potentials, right? E naught. Okay? So now, this is gaining electrons. Gaining electrons is reduction. So that means it's the cathode, right? So see the logic here? This is a point of logic that can be confusing because you just have to memorize it in a sense. Where oxidation is taking place is the anode. Where reduction is taking place is the cathode. So the logic I'm using is that they gave me this equation. Now I had to add the number of electrons to make it balanced, but they essentially told me what was happening here. I figured out that that's oxidation, so that's got to be the anode. They gave me this equation here without the number of electrons, but I was able to figure it out by balancing it. That's reduction, so that's got to be the cathode. The way that often people remember it is that oxidation starts with a vowel, and so does anode, right? These are both vowels. So you just remember oxidation equals anode. So in this case, you're taking the reaction, which is oxidation, and then from that inferring that it's the anode. Of course, the other one would have to be the cathode. You can have 2 anodes or 2 cathodes. If one's the anode, the other one's got to be the cathode. So now we got our voltage. Our cell potential is the cathode minus the anode, so that's minus 2.89 volts minus a 1.5 volts. Now you might say that seems odd because when you do that, you're going to get minus 4.39. Is that right? Let's check. Minus 2.89. So 2.89 minus a 1.5. Minus 4.39. And you're like, wait a minute. Didn't we say in the earlier section that when you do a galvanic cell, you got to get a positive voltage? And that's true. The fact that we got a negative voltage means that it's not a galvanic cell. All right? It's not a galvanic cell. It's non-spontaneous. And so later in this chapter is a discussion of what are called electrolytic cells. Electrolytic cells are ones that use electricity to make a non-spontaneous reaction occur. So the fact that that cell potential is negative means that this is a non-spontaneous reaction. If it's a non-spontaneous reaction, that means we have to put energy into it to make it happen. But we have that ability technologically. So now we got our cell potential, our standard cell potential. We calculated it. Now we can go back and do this calculation up here. So what's N? N is the number of moles of electrons transferred. Just so you know, it's that number right there. Of course, it's got to be the same. 6. So just put a 6 in there. Okay. Sometimes people put moles in there, which is fine if you want to write 6 moles or just 6. It doesn't really matter. It will change what the units are. You're either going to get the absolute energy, which is in joules, or you're going to get the intensive value, the number of joules per mole. Doesn't matter that big of a deal, quite honestly. So now it's minus 4.39 joules per coulomb. Isn't that interesting? We already got the units, joules per mole, because I didn't put moles in there after the 6. So 4.39, I think we have that number, minus 4.39. That's already in our calculator. So times 6 times 96,485. And again, if you want to use 96,500, that's fine. You get minus, oops, I forgot the minus. There's also a minus. So plus Oh wow, look at that big number. It's 541,000. So that's 2.54 times 10 to the 6. 2.54 times 10 to the 6 joules per mole. There's our standard. See how it's positive? Positive means non-spontaneous. Okay? And so keep in mind the sign convention. For delta G, positive is non-spontaneous, negative is spontaneous. For E cell, it's the reverse. Negative is non-spontaneous and positive is spontaneous. And the way you can tell is this right here. Whatever this happens to be, positive or negative, because you're multiplying it by this negative here, it's going to change the sign there. Okay? Now, if you want to convert it to kilojoules per mole, that's perfectly fine. You would just divide it by 1,000, and you'd get 2.54 times 10 to the 3 kilojoules per mole. Again, it's positive. It's a non-spontaneous. We would have to put energy in to make this reaction occur.